Hi everybody. Thank you for coming. Thank you for being here. I'm going to be speaking about distributed tracing. This talk is going to be sort of from the point of view of in the trenches, from the platform side of how do you actually make distributed tracing part of your platform, and how do you do it at scale. Before I begin, I just want to quick thank the SREcon board, and specifically my friend Nora from Netflix, telling me that I should submit for this. So I work at Jet. What's Jet? Jet is an e-commerce website, and if you're unfamiliar with the term e-commerce, all that means is a website where you buy stuff. So you can buy toilet paper or cat litter or really anything that you want. And we do groceries, and the real cool part about Jet is the bigger the cart you build, the more you save, which is a neat feature. And yeah, I mean, I use Jet, and I like my job. So it's important to keep in mind our e-commerce background here, because I think it really informs the conversation in terms of what types of actions that we care about tracing. And we'll get into a little bit more about that, but keep that e-commerce in mind. So a little bit about me. My name is Gina Maini, rhymes with linguini, and I'm a senior platform engineer. And basically my team is responsible for releasing a library every 2 weeks at Jet, and that's a library that all the rest of engineering uses. And yeah, there's my Twitter. Feel free to @ me for questions, or if you want to talk to me at happy hour about tracing at your company or stuff not related to tracing. These are some other core contributors, people who influenced this project greatly and brought their ideas and their thoughts to it. I just want to give a shout out to them. So when we're talking about Jet technology, there's a lot here that makes us really special, and especially for a retail company. So we do event sourcing, which is something that you may not have heard about. It's basically when your source of truth in a given system is the event. So what this means at jet.com is when you check out, you might be doing a lot of these different functionalities. So, you go to jet.com, you add cat litter to your cart, you click checkout, and all of a sudden in the background, there's all these subsystems that are reserving inventory and processing a credit card, and all of these kind of comprise checkout. And they're all important to checkout. But how those events propagate through the system is how we compute state. So maybe in processing a credit card, you have credit card update requests or reserve credit card requests, and those become events, and as we process those events, we determine a state in the system. The credit card is now this, it is valid, we have processed the transaction. So we also use F#, which I'm sure a lot of you haven't heard of. It's a functional programming language made by Microsoft. And this language is a very close twin of a language called OCaml, which is my background. OCaml is in a family of ML languages, ML not like machine learning, ML like meta language. Don't know why they chose that. I think it was like, the 60s or something, and they were into that. But anyway, it looks very similar to Haskell. It's got a lot of pragmatism to it and some really amazing features that we'll talk about later. But basically, you get an object system, but it's functional. You can have while loops and for loops, but you can also have monads. So it's kind of a total package, if you will. And it runs in the .NET runtime. So we're multi-region. That's another interesting thing about Jet. So yesterday, my coworker Andrew Duke gave an amazing talk on how Jet does failovers every week. And that's really, we one-click failover. That's what we do at Jet. So thinking about how to architect for multi-region, and especially lowering the overhead of knowing how to fail over for developers is core to my team's mission. Also, this is going to be really coloring the entire talk, but our communication style at our Tier 2 and Tier 3 services, so all these auxiliary inventory updating and updating search and all of this sort of background work, that's all happening asynchronously at Jet. You're writing these events to a bus, and later some downstream service is pulling these events from a bus to compute some state or to snapshot or do some other work. We're hosted in Azure. Not surprising, we're competing with Amazon, but also we use .NET, and I think it really makes sense for us to work closely with Microsoft, considering we use F#. We also get to drive feature development for a lot of their different databases, and we work closely with them, specifically on a product called Cosmos DB, which relates to this talk as well, but we'll get into that. And yeah, my team is the Marvel team. Just threw it up there because, Jet does, every engineering team at our company is a different superhero, which seems like a good idea, but, when you start on day one, you're like, wait, but who's Prof X? And how does Storm relate to what I do? It's very strange, just like you're a character in a comic. So why does Jet care about distributed tracing? Why even invest man hours? What problem are we trying to solve? So this kind of goes back to what I was talking about with these sort of distributed actions like checkout or maybe updating inventory or reserving a credit card. These are all different actions that might comprise larger actions, but also we want to know about them, and that involves multiple systems. It might involve multiple companies, and it can be hard to determine causality in these big actions. For example, if it's just your service, okay, your service is crashing in a loop, it's saying missing method exception in the call stack, boom, we know the cause, missing method exception. But in a distributed action, is it the search team? Is it Walmart's data ETL job? Is it, right? I mean, we've got so many different components owned by different people, it becomes really hard to determine what happened. So this is a type of a query we want to answer with distributed tracing. So show me all inventory updates which failed for a given merchant. So let's unpack that a bit, right? So what is an inventory update? Well, we don't know yet, but it's something that can succeed or fail, right? I mean, it seems like that, right? So okay, we know these actions can succeed and fail, and apparently we want to do a join or a group by on a merchant, right? We want to know for each merchant what is that failure for that inventory update. So that's a really complex query. It involves a lot of moving parts. So how can we go about determining how we would do a distributed tracing project just that traces this flow? Well, you might go over to the merchant team and you might say, hey, can you draw me a diagram of what your system does? What do you think it does? And they might produce something that looks like this. So the merchant being the user, and let's just do a quick aside as to what's a merchant. That might be you might be thinking merchants from Civilization 5 or something, what am I talking about? These are just third-party vendors like La Croix or Nike or people who sell shoes or whatever on Jet. And so when they want to update a price of their shoe or their bubbly soda, they have to go into our merchant tools and update it that way. So that is happening over a request-reply RPC style interaction. They're updating in a GUI, it's hitting this merchant web API, and synchronously they're getting an acknowledgement that yes, it's been updated, right? And now this merchant API is somehow writing to this catalog over a message bus. So that seems like a different style of interaction where we're not getting an acknowledgement. And then we're writing asynchronously to some Kafka topic, which Kafka is just a tool for distributed logging. So okay, we're writing to this log to index a SKU, presumably, and then, okay, this is getting published in search over a message bus to Elasticsearch. Okay, great. So merchant updates their SKU, and now we see it in search. This is what the flow is. This is what we want to trace. But this graph is useful, but, again, like I said, how would you determine causality, even if you were working on this system? Let's say you're the merchant API team, and a merchant calls you on the phone and says, hey, I don't see my SKU appearing in search. You don't know that the Kafka cluster, that your topic is borked, right? You don't know about that. But what you do know is you're not seeing it in search, and now you've got to call 2 other companies to figure out why your SKU isn't there. So we can also take this same view of that graph by kind of domains, right? You could think of domains with these edges being these schemas or services that they're communicating about. And here we kind of have a visualization where there are different service domains. Okay, we've got a user, we've got the merchant API domain, we've got the catalog domain, and we've got the search domain. And what I've done here on this slide is I've sort of color-coded these arrows. So the yellow here is a different style of interaction than the green, right? And we haven't really talked about that yet. The next slide is there, but we can talk about this. Okay, there's an update SKU flow. It enqueues that update dequeues to the catalog, which publishes to that topic, and then up to Elasticsearch. So that's another way we could view this same graph. And then we kind of layer the communication style on top of that and what events are actually happening at every step in this trace, we kind of see a more granular picture, right? We see, okay, there's starts and completes. We just made this semantic up, but you can think of an action as comprising a beginning and an end. Sounds pretty straightforward, pretty understandable. But when this user talks to that merchant API, they begin a span. Maybe that merchant API calls a client in HTTP to enqueue this request and respond back with an acknowledgement when it's been queued. And now we've asynchronously started. But these events, because they're asynchronous, we might not come in order. The timestamps might be delayed. There might be vast pauses between them. But basically, this is still the same graph. And I threw in maybe they would want to have an info event in here. Maybe that's relevant to their flow, something that you can't exactly see with their communication style. So we can also view it this way. As time moves, there are tracing events that happen that represent that running trace, right? And so we can just view it like an event log. Well, that sounds pretty similar. Jet does event sourcing, so this sounds like the shoe fits. Okay, let's do it this way. Okay, so I want to event source tracing data to be able to do causality and understand, how my actions move in a system. What can I use today in the ecosystem? Well, nothing really fit all of our use cases. And that was something that was really hard for us to find. But there is a lot of stuff that exists today that's worth putting on a slide for you guys. So this is all like pretty industry standard. And I see a lot of people taking slide photos, totally welcome to. I will make sure that these slides make it online as well if you want to grab them. But basically, these are the big players in the ecosystem. And a lot of them really focus on allowing you to have sort of time series visualizations of RPC, which, request reply channel type communications where it's like HTTP. And you can kind of get like a latency time series view on that, which is useful. But again, at Jet, we're doing mainly asynchronous at our tier 2 and tier 3 services. These ETL jobs might take a day. What's the usefulness of that? I just want to know if it's broken. Like, just tell me if it fails. Like, I don't care the latency may be more noise. I'm looking for more signal. So we found that most of this stuff, while really good ideas, and we totally pulled from these ideas, I would say we're OpenTracing compatible 100%, and we've done that for kind of a business standpoint. But we sort of had to go off into a bit of uncharted territory as we sought to meet needs at our company. So we decided to make like a custom distributed tracing platform in F#. So that meant writing F# client libraries. It meant publishing a way for people to log these tracing events and basically managing the service that indexes and provides querying on that. Maybe it's alerting, a dashboard, right? That's what we provided as the product. So what could go wrong? Like, what would be hard about doing all of this, right? Well, there was a lot wrong. There was a lot wrong. So we started in this endeavor. And it was a really bumpy ride. It was super hard to get people to onboard. And, why am I even talking to you guys about this? Why am I talking to you if we had so much failure? Because we turned our failures into wins. And, I think failing is what made us know what our users wanted, and I, treasure the users that bang down your doors, treasure those people because they make you a better engineer and they make your product better. So what kind of mistakes did we make in our V1 of our tracing library, right? Or really more than a library, an entire platform. So what did we make a mistake in? So we tried to think about how can we make tracing baked into the platform from the get-go. We didn't really know how to structure the semantics, but we knew bake it in from the beginning and just make sure everybody does it, because that's how you bring value in tracing, is you trace all the things and then you have all the value. But the funny thing about that is you can't actually put more work in your sprints than is physically possible. That's the weird part about how that works. So we needed to start to think smart, especially since there's only, for the majority of this distributed tracing projects, it's been me and, a couple other people. So, we have limited time. How can we provide the most impact and be effective, right? Have this be an effective project where people can really use these tools. So we in the beginning, we requirement gathered from business and developers alike, but really developers were interested in sort of this end-to-end SLA question. They wanted to get automatic alerting on anomalous behavior, and they wanted it to work like Splunk. So, but when we talked to business users, what they wanted was high-level graphs that showed dependencies and topology hierarchies, and developers were interested in dependency needs in the sense that if I change this schema, what schemas break downstream for me, that sort of thing. But business users wanted to understand what is the state of the running system. And actually, these are different front ends, these are different back ends, and they're different use cases. And so in designing for both of those, we took on too much to bite. We should have chose, let's just solve end-to-end SLA, and let's move on to another problem. So the other thing we needed to do was find people who wanted to trace things, really find sponsors in this company who want to see problems solved with distributed tracing. So it was people who identified with the mission, understood the challenges, and wanted to help us roll it out. So we ended up finding advocates in the end, but in the beginning we sort of built things in an ivory tower. That's never a good plan. The other thing we did in the beginning that wasn't good is our wire specification was complicated. We chose a really complex solution. I'll show you an example of it in the next slide, but basically we wanted to bolt on a lot of concepts from OpenTracing, but also some of our own. Actually, I'm just going to skip ahead now, let you guys see it. So we had a bunch of stuff. And if you look at this record type here, this is F#, this compiles, but it looks like a JSON object, so I feel it's safe, you know. But you can see these field names are like kind of terse, right? Like what's a correlation ID? I don't know, something to correlate? What's a payload schema URI? You know, like something about a payload, something about a schema, and something about a URI. We had a lot of devs come to us and say, look, how do I fill out these fields? Like, I don't even know what schema I use. You know, like this isn't even owned by me, this schema. So if I set the wrong thing, like what happens to my tracing data? And we were kind of like, well, you know, it doesn't matter. Just like add what you need and we'll figure it out later. And they were kind of like, what? Why am I doing this? Like, why are we ushering in schemas on top of tracing? That's so confusing. And then we also had this idea of P tags and M tags, which basically means process tags and message tags. But, you know, in this tracing question, you know, what is a message, I think is an open question for developers. And then what is the process entirely? They may not be aware of what that larger action is that they're comprised of or who owns the tracing for that action. So what metadata they want to propagate throughout the whole trace versus what metadata should be scoped locally. That was like a complicated question for developers, but it's actually pretty straightforward, right? Like some things like IP address or machine name or service name, those things you'd want to be locally scoped, maybe to an operation or one span. But there's some metadata that you want to carry throughout the entire lifetime of the trace, like merchant ID or SKU ID. So it became hard for them to know what fields they need to fill out where. And we had documentation, but turns out people are busy and they don't really read documentation. So we really just needed something simpler, and really they shouldn't even be considering like what the underlying format was. We should just build tooling that automatically did all this stuff for them. And we'll get to that, and that's what we eventually did. But basically, we got around a lot of this metadata carrying in the actual wire format by just emitting it as events. So we created separate event types that just allowed you to decorate trace information. And that was way better because then we didn't have to put trace information in an actual like HTTP header, which is kind of like, why do you want business sensitive information in your HTTP header? Maybe you don't want global mutable state where you just overwrite these tracing values in the header and now you've lost tracing information. So we chose a real minimalist wire specification that really just had a trace ID, so same name as OpenTracing, a little easier for people to buy into. An operation name, it doesn't have to be global, it just talks about what your service does. And then tags. Now the tags we sort of ended up auto-populating from our library, and basically as these operations would run, we would auto do span out calculations and hook into other metadata about the service as it ran to kind of give them value out of box. But in the beginning, we sort of expected them to choose their metrics. But I think it was, you know, like that's a lot of overhead. You're just hooking up this tracing thing. Now you've got to deal with like what this even does. And now I've got to think about metadata. It's like too much. So we made it super simple. So auto calculate span latency. And of course, in operation, you kind of get away with issuing time drift a little bit because it's the same clock that's issuing the start and the stop. So we got really good end-to-end SLAs on that. We integrated with so we use Nomad for containerized orchestration, and we use HashiCorp tooling for secret discovery and service discovery. So we integrated with that Nomad metadata, and all of a sudden, all of the service manifest definitions hooked into tracing. Big win. Another thing about the first version of the library that was really complicated for developers was F# is strongly typed. So that means at compile time, you have a lot of sense of what the state and all possible values will be, and you've matched on all of those possible values. So that means in tracing, when you deserialize a payload as an incoming request in service, that payload now becomes part tracing data and part actual payload, right? So you've got some header that you're extracting, and that has trace data, and then you have to carry that around in your service. So everything else that deals with that operation now has to have it. So you could do this a couple ways, right? You could have a local thread storage. You could have some shared global state that now all of these services have to pull from. But that becomes really difficult, especially if the service is processing in batch. Maybe it's taking in 100 traces, creating a new trace from them, and then shipping them off or something. We had a lot of sort of batch processing jobs, and so kind of fitting OpenTracing semantics onto that didn't really make sense. So we built in really great automagical functionality that worked with F# computation expressions. So computation expressions is a feature of F# where you can define it's basically syntactic sugar for monads, if that's not an unsavory word. And basically, on every bind of a computation, we were able to automagically calculate data for them. And that was really great, and they didn't have to change type signatures, really. They had to change one thing, and it was much easier. So we just did some type magic and some functional programming magic that allowed us to implement sort of a reader monad pattern. The other thing that we did was ship with multiple carriers that people cared about. So we requirement gathered after we picked the flows we wanted, and we said, okay, what disparate systems do we have to be have tracing compatible formats for? So that was Kafka, that was event streaming libraries that we make in-house. We have an in-house projection and replication system, so we wanted to make it compatible with that, and we wanted to make it compatible with other Azure databases over HTTP. So we wanted really specific roles and stuff that people could decorate and play with out of box, and just say, hey, I'm a server who talks to this other system. Boom, immediately they get tracing data out of box about that. So, okay, and the other thing we did was we also decoupled the need for F#. So we had a lot of people in the company. Our DevOps team writes Go, our data team writes Scala, and we have Nginx, right? Maybe you want to write a Lua script that does some tracing decoration of your incoming requests. So all of those people were not going to use our client, but how could we maintain basically a similar format and not provide overhead when they're writing those clients? That became kind of hard, so we agreed that we would develop a system where when you emitted these events in service, they would write to a local file, right? And that would happen asynchronously. And we'd set up daemons to read these files and ship these telemetry events from these, trace information to our Kafka topic. So we basically set up a paradigm by which if you agree to use this telemetry event format and ship it to our topic, we'll do the tracing for you. And this was really great because it allowed people a lot of flexibility about what type of client they were using and how they wanted to trace their services. So this is an example of our telemetry event type. Pretty simple, looks a lot like the trace context type that I showed you earlier. Basically, it's a GUID, which represents a unique instance of the trace. It's got a type of event, so we gave structure around operations. We may not be able to know if the entire action failed from one operation, but we can know if the operation failed. So we structured it to have either a start or complete, or maybe they want to have a custom tracing event that they define. We have a timestamp, pretty simple, and some tags that we populate for them. So inside of this time log view, we can now have some structure to these events that kind of give us generic tracing information. Maybe we have a merchant ID, we have an operation name, which we can wait for a completion on, and we're good. It sounds like we're ready to go. We're ready to do event sourcing of this telemetry data. Oh wait, indexing and querying. How the heck do we do that? So this became a real big problem because how do you know if your graph is deviating from normal? Pretty difficult if you don't have a structured definition of what checkout is. If you don't have a file that defines this is what checkout is comprised of, it is a successful SLA within these boundaries, it's really hard for us to sort of per team and per flow sort of implement. It's almost like you need a workflow engine to determine, here's the incoming trace data, let's apply some sort of rubric and validate that it's anomalous or not. So that's really hard because then someone has to maintain these graph manifests, right? Like some TPM or someone on your team, or maybe you just don't go this avenue and you event source everything and somehow use machine learning to determine, this is normal or not. But it's hard to set like an alert or a pager duty about that. You know, if you're waking up at 3 a.m. for some machine learning system that tells you your graph is deviating, you know, like that's like very esoteric. Like how am I supposed to get into that and debug that? So what we decided to do was take a different approach. We weren't going to have people write or manage manifest files. We were just going to allow them to tag their ASTs. So the abstract syntax tree is accessible in F# via attributes. So you can decorate your AST with different attributes that have names of these operations and maybe some other tracing information. And when they compile those programs and deploy them, we have scripts that scrape that and can generate a graph definition basically from the actual code that they run. This is a huge win because now I don't have to manage a definition file which may or may not map to reality. I have this tracing information at compile time of what this service does in a graph, in terms of what the graph is. But also, like, this is still experimental for us. We're still determining what the limits are and how we're going to use this type of technology. But one way we allowed people to, in the meantime, sort of get massive value was we took, let's skip to the system diagram here. So in the system diagram, you can see that little, little symbol there is a microservice, and it's emitting to a log file these tracing events: start, stop, info, right? And it's going to a log file which is being replicated by FileBeats, a daemon, to our Kafka topic, which is being indexed by our X-ray service. By the way, long story short, the project's name is X-ray. Can't believe I haven't mentioned that yet, but there you go. And it indexes into Cosmos DB. Cosmos DB is a document database from Microsoft. The cool thing about Cosmos DB is it has a functionality of a change feed. So when you insert documents into DocDB and you listen on a collection, you can get a stream of those incoming documents that come in, which is pretty neat. So what you can do is create a projection service which snapshots topology. So you can say, okay, I'm going to window on any key value like merchant ID, SKU ID. As they come in, I'm going to snapshot them, bucket these individual trace IDs inside of there, and boom, I've got like a snapshot of my system state. And we sent that all to Splunk, and we sent it in 5-minute intervals, a topology snapshot to Splunk. And we allowed developers to window an alert the way they wanted to, which is essentially what they wanted to begin with. You know, if your users tell you explicitly, I want Splunk, you know, it's like you kind of have to like really listen to that. So yeah, we just had well-defined semantics around operations. We basically used snapshotting of topology to derive most of the type of dependency understanding SLAs, as well as those individual SLA hops. Yeah, and so once we kind of ingested all of this into Cosmos DB, we put it behind a query API so you could query over, you know, by trace ID or by merchant or whatever key value you wanted to get kind of a time series view of those tracing events, like a call stack basically. But also, like, that was useful, sort of. But what people really wanted was, you know, from the business standpoint, they wanted to be able to visualize it. And from the developer standpoint, they wanted to be able to do postmortems that were more visually appealing. So we thought, okay, let's make a dashboard. So we've done like 3 iterations of this dashboard. And really the pain point has been, you know, like time series span is not a really good fit for what we do. We need hierarchical views. We need views where we can slice a graph by multiple indices. We want to look at domain to domain, service to service, machine to machine, and like user to user, right? We want all different types of graphs that we can explore and visualize and tracing. And actually, this is a really great, you know, and we're innovating in this area. We brought in a lot of people to focus on building a great UI that allows us to do these types of investigations. But I think multi-tree viewing of these traces, that's somewhere where I'd love to see innovation in open source and industry, because I think there's not really a good multi-tree diff view. I mean, it doesn't really, like, It's not easy to process this much information in a UI and be able to do like postmortems on it. So in the future, like where are we headed? So, okay, our tracing system today can support the flows that we want to trace, and we're meeting the needs that we want to meet for developers. Great. But what's next? I think for tracing is a lot of overhead for people to think about, right? It's a lot to think about, and frankly, people want to just think about logging in the generic sense. I just want to log metrics, or I just want to log info, or I just want to log like everything to one log, and I want to have different backends, and I want to have different ways that those are maybe snapshotted in process or aggregated, and we're going to provide mechanisms for people to do that. So tracing, for me, the future of tracing is less visibility to the developer and more out of box. And also, I think schematization is going to become huge for us in the tracing epic. You know, we really tried to do it in the beginning, and we shouldn't have. But now we're a more mature project. I think schemas, if you will, are really the edges between your nodes. It's super important to understand what those schemas are because they really affect your dependencies. So yeah, and I think you'll see this project in the open source. Like Jet is moving a lot of its internal stuff to open source, and we're really putting a lot of inertia behind that. So yeah, look for it. And some lessons you can go to the bank on. Get sponsors, get people who want to trace stuff and really empower them to help you complete the mission, because it's a cross-team collaborative project, and you're going to need to knock on different doors at different companies. So be sure you have some allies. And this project takes a lot of time and requirement gathering. So make sure you do those steps. This is like software engineering 101, but I think this type of project typically is thought of as more R&D. And most places I go and I ask to see their tracing tools, I'm like, yeah, but is anyone using this flow? Is anyone actually solving problems with tracing? The answer I tend to get is, no, it's kind of like a cool experiment. So the more you can get away from that, the better you're going to be. Anyway, come find me if you want to talk. I'm always happy to talk. Here's some more reading I included on these slides, stuff that I think, really worth perusing. And yeah, this is the time for questions.
Hi, thank you for the talk. In your data structure, you had a field for specifying the operation string. How do you coordinate between like multiple clients if that's a user definable string so that there's not like namespace collisions in your final database?
Yeah, that's a really good question. We haven't really gotten around namespace collision issues, not entirely, right? Operation names are more just that your query would have events that weren't yours. Right? That would really be the bottom line of what would happen. And then based on service name, you can do a union by, I'm looking for this service with this operation, right? So it's really a question of you just uniquing out your data. But the name collision problem, while annoying for windowing and alerting, is less of an issue for our devs. But yeah, it's going to be an issue in the future for sure. And how we do that, I think, really is kind of where the schematization is going. Let's codify what these operations are. Let's codify the schemas they communicate on, and all agree on that. Whether that's a type provider, that's an F# thing, or whether it's an Avro schema, like that's a conversation we're going toward, and that'll help us with the naming collision issue. Right now, you're just getting events that aren't relevant to you, but if you see that once, you can exclude it with kind of like a union in Splunk, basically. That's the real answer. All right, are you guys hungry? We're going to go eat, right?